Thank you very much for the kind introduction, and thank you very much for having me here. It's a pleasure to tell you about some of our recent experiments over the past years that we've been carrying out in Munich on rather diverse range of topics. So what I planned today, we have to see if we get through everything, but give you a little bit of a flavor of the things we have been doing and the questions, physical questions we have been addressing in these ultra-cold atomic systems. So first I would like to start out with an introduction into the field, talk a little bit about something that's of course very much connected to the most recent Nobel Prize in physics, topological matter, and how we can actually probe that using ultra-cold quantum gases, different ways, either developing new interferometric techniques or using these quantum gas microscope experiments that I'll show you next. Then there's a completely new topic, I think, which has been taking storm, the field of condensed matter physics, which is called Manybody localization. It's in fact the old problem that Philip Anderson tried to address already before, but it very much connects to a lot of actually fundamental questions also in quantum information theory and statistical physics. And again, I'll try to show you a little bit what we've been doing in the cold atom context in this direction. And finally, if I do have time, but we really have to see, I would love to talk about Rydberg atoms, because Rydberg atoms really, this is the place to talk about Rydberg atoms, if not LKB, where else? And so I would like to show you some recent progress on these Rydberg-dressed quantum gases. Okay, so let me start and motivate just briefly the research we're doing. Of course, everything we're doing is driven very much by trying to understand quantum many-body systems. They are, of course, complex. There are different kind of things going on there. We have very many complex interplay of phenomena masking several effects. So I'll maybe just stop for a moment. All right, that's okay. And of course, you know, what is trying, apart from all the technological things that you can do with these systems if you understand them, of course, our interest is more directed to the fundamental questions associated with these, to the fundamental scientific questions. And of course, it builds a lot on work, famous work, you know, going on in the field of quantum optics. The most recent Nobel Prize in that field to Dave Winan and Serge Haroche, of course, to being pioneers in controlling single atoms, ions, and photons. And we want to take this to the next level in trying to build upon these advances, in trying to assemble controlled many-body systems, in trying to now understand, look at questions of, complex questions of, you know, complex quantum matter. And this is, of course, not pursued only in the systems I'm going to introduce to you, these crystals of atoms, but of course, other people are doing this as well. The ion trap community is very successful. Superconducting device community is very successful in doing that. So I think almost everybody in the field of quantum computing, quantum simulation is trying to address many of these similar questions. It actually starts out with this famous paper from Richard Feynman, but let me skip that and go directly to the heart of what we're doing and just very briefly introduce the system that we're looking at. So we're trying to load ultra-cold atoms, or we load ultra-cold atoms into crystals of light. And here's a beautiful pattern that was actually taken by Ted Hensch just to show you the beauty of these crystals of light. This is a very simple experiment he did. He took a laser beam, expanded the laser beam. Okay, so there's a big laser beam, and this big laser beam is hitting these apertures. So there are 5 apertures here. The laser beam passes the apertures, and with the lens, you focus the laser beams behind. And of course, what you get is the interference pattern of those 5 these openings that you get there, the light passing through those 5 openings. And this 5-fold case, you actually get a quasi-crystal structure, as you can see. So this is the beautiful interference pattern that emerges just from light hitting these apertures here. And it just shows, you know, that this structure is not only aesthetically pleasing, but we have very good control over them. They are completely defect-free. And what we do is we essentially we place very gently cold atoms into these structures and try to observe the behavior in these artificial crystals of light. So these atoms are held in these light structures, and we try to look at their behavior in these light structures. Now, how is this complementary to what real condensed matter physicist is doing? And actually, there's something on this slide. You can't even see it. I hardly can see it myself, but I know it's there. You'll see it in a second. Well, actually, it's here. You can see it maybe. So this, let's imagine this is a real crystal, real material with the spacings going on. And in essence, of course, what people building better X-ray microscopes are doing, they're trying to build very good microscopes to look into this very small crystal. And what we're doing is something exactly the opposite. We're trying to blow up this crystal by a factor of 10,000. Instead of having angstrom distances, we go to micrometer distances. And now these systems become accessible to optical means, and we can look into these optical crystals. So we're essentially blowing up this crystal to large scales, 10,000 times larger than what you have in real materials. And this, of course, has many implications. You might ask, first of all, can you even hope to observe condensed matter behavior in such systems? But then, of course, you remind yourself that the only thing that matters to see collective quantum behavior is, in essence, the ratio of the de Broglie wavelength over the interparticle spacing. So if we, on the one hand, make this d 10,000 times larger than in a real crystal, if we can make lambda 10,000 times larger at the same time by cooling to lower temperatures, we can be in the same quantum degenerate regime as we are in real materials. So we can, in essence, observe many-body physics at these very dilute densities, observe phenomena that we typically only know from real materials at kind of 10 orders of magnitude larger densities in these systems. Of course, the price we have to pay is that everything happens now at few nanokelvin compared to millikelvin to kind of several hundred Kelvin here. Another advantage of the approach, if we look at time dynamics, when you go to these large scales with these low energies involved, this of course also means that everything that happens here on a femtosecond, attosecond time scale will happen on this case here, in this regime here, on a kind of millisecond time scale. So time dynamics is very nicely accessible in the systems, and we're making a lot of use of that in the experiments. Okay, so let me start with the first topic then which we analyzed. This is ultra-cold topological matter. And I want to give you two examples of how we can probe that in the experiments. And this is, of course, very much connected, as I said, to this year's Nobel Prize, especially to David Thouless's work, which I'm going to first touch upon, and later also connect to Duncan Haldane's work a little bit later in the talk. So where do we see topological effects? Well, the most prominent cases we know are, for example, the integer quantum Hall effect, topological insulators, or if we talk about interacting quantum systems, for example, the fractional quantum Hall effect. And let's stick for a second with the simple systems, the simple band systems, and try to understand, recall again, where this topology actually emerges from. And for that, we have to remind ourselves how we describe the eigenstates in such crystal structures. Well, they're, of course, Bloch waves. And they give rise to scalar features, which is just a dispersion relation. It links the energy to the momentum of these states in the lattice. But on the other hand, we have geometric features. And these geometric features are intimately tied to the wave function. So we can define, on the one hand, something that we call the Berry connection, which is taking the gradient of this cell-periodic Bloch wave function overlapped with the Bloch wave function itself again. And if we take the curl of that, or the generalized curl, because this can be a multidimensional parameter space, if we take the curl of this Berry connection, we can define something that we call the Berry curvature in the system. And these are the geometric features that can give rise to topological features, and these are things we would like to measure in the experiment in new ways. So how do you measure that? That's the first question. How can you measure these geometric topological features? Well, the first thing you can do to measure these topological features, or these geometric features, is, for example, that you take a closed loop in your parameter space and look at the phase shifts that you pick up under such a closed loop evolution. So let's imagine this is the Briand zone of your system. You start out with some k-space point here, and then you move along a closed trajectory and come back to the same point here. So what happens now for the wave function of your particle is that on the one hand you pick up a dynamical phase shift, of course, but on top of that you can pick up a geometric phase shift, and this geometric phase shift will be just the line integral of the Berry connection over this closed contour divided by 2 pi. Now there's a very special contour you can take, and that's given if you take the contour around the entire Briand zone of your system, of your crystal structure. That would be written down here. So you take the line integral over the Berry connection over this path divided by 2 pi. And you can actually show that this number, this is a topological invariant, and this is the so-called famous Chern number of your bulk material. It's a bulk property because it just depends on these bulk eigenstates that we have in the system. Okay? And this, again, if we apply now Stokes' theorem, you can see that this is equivalent to integrating the Berry curvature, which is just the curl of the Berry connection, over the entire Briand zone. And this is exactly what a condensed matter physicist would do if you take an integer quantum Hall system. You have an insulator, you have a Fermi sea, which fills all the states in your band. So with this filled Fermi sea in your band, you're effectively integrating over the entire Briand zone. So you get the Chern number. And this Chern number here, if it's non-zero, we say that the system carries topological features. This Chern number actually links the number of edge states you have in a finite size sample. And this was the famous work that was one of the things that was responsible for getting the Nobel Prize to David Thouless. This was expressed in his famous paper in 1982, which linked this bulk topological invariant to the quantized Hall conductance that people measure in the integer quantum Hall effect. And you can simply say the number of edge states that you have is determined by this Chern number. Each of these edge states carries a quantized conductance of E squared over H. And this explains why you have the quantized Hall conductivity in the integer quantum Hall effect. Now you see, one thing we can do with atoms, we're not restricted to moving particles around the Brillouin zone here. We can move them basically around any trajectory, and that's a big advantage that I'll make use of in a second. But I just want to show you another method how we use this, and this was actually done by Monika Eidelsberger, who's also here in the audience, has been spending a year now in Jean Dalibar's group, how you can measure this Berry curvature in another way and determine this topological invariant. And this is coming back to the basic semi-classical equations of motion, how a particle moves in a solid. So you see on the one hand, you have the force, which is just the gradient of the potential here, which just gives us the electric field, and the Lorentz force of the particle. And then you have the velocity of your wave packet, which is just given by your group velocity. This is the dispersion relation of your band, so it's just the group velocity. And you have this term here too. And this term here, actually, as a side note in history, is interesting to note that this was already expressed in the famous 1954 paper of Karplus and Luttinger, but later it was completely forgotten again. So if you look at the standard textbooks of Ashcroft and Mermin, you will not find this term, for example, in the semi-classical dynamics. Yeah? But you see, actually, all these equations just become fully symmetric if you add this term. And this is what we call the anomalous Hall velocity that you pick up when you expose a particle to a force in this solid. And if there is a Berry curvature here and you apply a force in this direction, this will lead to a transverse displacement, to a transverse velocity the particle picks up, given by this Berry curvature. And that's one way how to actually measure this Berry curvature in the experiments. And this is what Monika and colleagues did in the experiments at the time in Munich. And to show that from this you can actually determine this Chern number that I explained before, which gave rise to this measurement of the Chern number of 1, which we expected to be 1, without making use of any edge states. So it was the first time you could measure this Chern number in kind of a system without making use of edge state transport in a non-electronic system. Actually, I want to move on and tell you about a second method, which I think is even maybe a little bit more striking and makes really nice analogy between the Aronoff-Bohm effect and how we can interferometrically measure this Berry curvature in the experiment. So let me remind you again of the Aronoff-Bohm effect. So you know it's one of the most foundational effects we have in quantum mechanics. Usually explained that if you take an electron wave packet, you split it, you move it around a region with a certain magnetic field, and you recombine the electron wave packet again, then you get a phase shift between these electron wave packets arriving at this point here, and this phase shift is going to be proportional to the magnetic flux enclosed in this interferometer area. So that's the standard Aronoff-Bohm effect. Okay, so this is the vector potential of electrodynamics, this is the B field we have, and now I can write down exactly the same expression for the Berry curvature that's present in a solid. So we can now take the Berry connection here, and if we take an atom, we're now in momentum space. If we split the atomic wave function in momentum space, we move it around a region with Berry flux, then the particle, the wave function of the particle is going to have a phase shift here, which we can measure, and this phase shift is going to be proportional to the enclosed Berry flux in this interferometer area. And you can see actually the equations are precisely the same that you would write down in electrodynamics. Okay, so you have exactly the same equations. Now you've built a momentum space interferometer that doesn't measure magnetic field, that measures these geometric properties of your bands, that measures this Berry curvature in your system. Okay? The test case we use to study this is graphene, hexagonal lattice. Graphene has an interesting Brillouin zone. So this is the Brillouin zone of graphene. We have these gamma points, the K point, K prime point. And if you remember, graphene has these Dirac cone dispersion relations, this relativistic dispersion relations precisely at these K and K prime points. What it also has at these k and k prime points is actually a singularity in these geometric features, the Berry curvature that I mentioned before. So the Berry curvature, the Berry flux is actually concentrated to values of pi and minus pi as delta functions at these k and k prime points. Okay, so you really have delta function localized Berry flux at these singularities, at these Dirac points that you see here in the experiments. And that means, of course, in a transport experiment, you cannot measure that. Because you have zero measure in momentum space, if you move particles through this region, you will not be able to hit this kind of and see kind of some effect. You have, because simply this has just zero measure. But in an interferometric way, we can measure it. So what I want to show you now are results where we build this momentum space interferometer. We split the wave function of the atom. We move it around these paths, and we recombine it here. And what I'm going to show you is when we read out the phase of this interferometer, how that changes as I change the endpoint of the interferometer. So we're going to start with a diamond like this, no Dirac cone included. Then we're going to move to a point which includes one Dirac cone. And then we're going to move to a point where we have two Dirac cones included in the interferometer. And we just want to see how this phase shift actually changes in the experiment. And this is what we see. So you see this is the endpoint of the interferometer. This is the endpoint of this diamond. And you see as long as there's no Dirac cone included in the interferometer, there's zero phase shift. As soon as you hit the Dirac cone, you jump by pi in phase. This is this pi Berry flux located at the Dirac cone. And as soon as you have the next Dirac cone entering, it jumps back to 0 again because you now have 2 pi or 0 pi included in the interferometer area again. What's really quite striking when we did these experiments is how sharp this jump is. So here's the endpoint of the interferometer. And just by changing a few percent in momentum, the endpoint of this interferometer, you see this jump from 0 to pi occurs. And that, of course, immediately tells you that this Berry flux must be concentrated to extremely small regions in momentum space. And from the steepness of the curve, we could actually deduce experimentally that the Berry flux has to be localized to better than 1/1,000,000th of the size of the Brillouin zone in our system. Of course, that's the best we can do in terms of approaching this delta function that I said the system should have theoretically. All right, let me move on to another topic and come to topology in a different context of many particles in the system. And this turns to our quantum gas microscopy experiments. And before I explain them a bit more, let me first introduce the basic notion of what this actually means to do quantum gas microscopy on a wave function, on a Manybody wave function. So imagine you have some complex quantum system. You prepare some ground state or some Manybody state, and let's say this Manybody state is a superposition of different spatial configurations of the particle. Of course, there will be complex phase factors here, but let's forget them for a second. Okay? And now you make a photo. Imagine you could take a solid, a fractional quantum Hall liquid, and you could make a photo where you see all electrons in the system. What would you see? Okay? Well, if that's the state of your system, and you make a photographic measurement, what's going to happen, of course, is that the wave function collapses onto one of the constituent configurations in particle space. So in one shot of the experiment, you might see this configuration of the particles. But if you prepare psi again and make another measurement, then you might see any of the other configurations also, with the probability, of course, given by the weights of these amplitudes that we have here in front of these wave functions. Okay? That is extremely powerful because it means now you can ask very complex questions. You can start to ask questions, how is, for example, this particle correlated with this hole and these two particles over here and that hole over here? So you can really start to ask questions when you get access to these single snapshots of the wave function that are simply impossible to ask in standard condensed matter setups. And I'll give you an example in a second of how this can be used to reveal something that you cannot reveal in standard condensed matter setups. We also showed, at least in other experiments, ideas how this can be actually also done for currents. So in principle, you can also measure currents between bonds and thereby get snapshots of the currents, the quantum currents going on in such a Manybody system. Okay, and that gives you complementary information about the phase of these prefactors in the amplitudes of the wave function. So this is what this looks like typically in the experiments. So we have a very good microscope objective. with a high resolution that can take a photograph of the atoms in a single plane, a single two-dimensional plane of our system. And the way we start to see the quantum system is that we turn on resonant light, and this resonant light will be scattered by the atoms. That's exactly the moment where we make this measurement, this projective measurement. And then we see the atoms coming out, for example, like this. And you see that this is really a fantastic signal-to-noise ratio. You can see each atom, each individual atom here lighting up and showing you that we can really see these individual atoms in these lattices. We can also control them. I'm not going to talk a lot about that. We also have possibilities to control them. Here is just how we can manipulate them by shining a laser beam onto an individual atom and flipping the spin state of that individual atom. So you can, for example, make a line of atoms, a star, Neal antiferromagnet, or, well, okay, this just for fun, we made this psi out of 26 individual atoms in this optical lattice. Just to show you that we can really, you can tell me, I want to go into atom number 5543, and I want you to rotate the spin of that atom by 10 degrees. And we can do that, okay? And this is kind of the proof that we can do that. Recently, this has been extended also to fermionic systems in our Munich team, in Markus Greiner's team, Martin Swirlein's team, Stefan Kur's team. So many teams around the world, actually Joseph Tyveson also is here, who've been doing this now also for fermionic particles. This is just a photo of a fermionic band insulator showing that we can do this as well. The twist we have in our fermionic system is interesting compared to the other experiments, is that we combine it with a way to see all the spins also in these photographic measurements. And let me explain a little bit how we do that. So imagine you have now fermionic particles, spin ups and downs, electrons, spin ups and downs. You can have holes there, you can have doubly occupied sites, and imagine this would be the configuration of your electrons on this one-dimensional chain. So how can we see that in a spin-resolved way? If we just take a photo, we would just get something like this, where we see maybe there's a hole here, there's an atom here, but we don't know, is this a spin up or is this a spin down atom? We just don't know. Okay? How can we still resolve that? How we can still resolve that is that we take this chain, we split it into two chains with a double well beam splitter, and we do this under the action of a magnetic field gradient. So in essence, what we're doing is we're making a controlled Stern-Gerlach separation. We're making one line into two, but we're separating it under the action of a magnetic gradient field, such that the spin ups move into the upper chain and the spin downs move into the lower chain. So now you have, for example, all the spin ups sitting in this chain, all the spin downs sitting in this chain. And now if you make a photo of these two chains, you have a complete reconstruction of the original occupation of that single chain. For example, let me show you a picture like this one. This is the upper chain, the lower chain. Okay, this would mean no particles, a hole. No particles, a hole. A spin down, a spin up, a spin down, a spin up, a spin down, a spin down, a spin up, and a doubly occupied site. That would be the configuration we have on that single chain. And that you can directly see in these experiments, and you can fully kind of get the information of all the particles and holes and doublons in that single shot. So what can you do with that? Well, the first thing you can do if you have fermionic particles, you can look for antiferromagnetic correlations, a standard thing that also a normal condensed matter physicist could do. And if you look at this in the 1D setup here, look at this correlation function, a two-point correlation function. Actually, this should be I plus D, sorry, here. Then you see nicely this antiferromagnetic staggered configuration that you expect for a Heisenberg model. Okay? So that's pretty much standard, but now, and actually sometimes you get the beauty of seeing shots like this, okay, where it's really up, down, up, down, up, down, up, down. But keep in mind that for a Heisenberg antiferromagnet, even at t equals 0, this is a very rare configuration. The ground state is not at all like that. This is like the classical Néel state, but has a little bit of amplitude in your wave function, so sometimes you do see that state, okay? What else can you do? Let me show you something that's more complex that you cannot do in a condensed matter setup, and that comes down to the phenomena of spin-charge separation. So imagine you have this antiferromagnetic chain here, and you remove one particle. Let's say we kick out this particle so it leaves a hole behind. What can now happen is that this hole can move freely in this antiferromagnetic chain, and at the same time it leaves a so-called spin-on excitation behind, and this is what we call a hole-on excitation. The hole can move freely, and it leaves behind a spin-on kind of excitation. You can also ask, if you have a hole in the system, what is actually the ground state, the lowest energy configuration around that hole? Is it a ferromagnetic alignment of the spins or an antiferromagnetic alignment of the spins around this hole? And it turns out that the lower energy configuration around a single hole is an antiferromagnetic alignment of the spins. So if you would do this in a ground state of this hole-doped chain, you would actually find that around a hole, the spins should order antiferromagnetically. And not just what I showed you before, that you kick one out and they're ferromagnetically aligned. So what you see is what happens in the ground state of this 1D Fermi-Hubbard model, if you dope it with holes, is that each time you have a hole, you flip the parity of this antiferromagnetic background by sign. So let's say this would be a +1 configuration, down, up. And now when there's a hole, this is flipped to down, up, okay? Whereas if we would just kick out the hole, it would be just the reverse. So each time we have a hole, we get parity kinks in this antiferromagnetic background. And now let's see if we can, now I show you an example of already something that you cannot measure in a solid. We can do that. We can measure precisely that with our quantum gas microscopes. We can look how are the spins oriented around holes. So we look at the spin correlator at site I and I+2, conditioned on the fact that there's a hole in between. How are the spins aligned, conditioned on having a hole in between? That's a 3-point correlator already, right? It's something you cannot measure anymore. And if you do that, you see compared to the undoped chain, where you have this positive correlation for distance d equal 2, you see the sign indeed flips in the case when we have this hole in the ground state configuration of the problem. So indeed, when you have a hole, the ground state here gives rise to antiferromagnetic correlations around this hole. You can actually see this even more striking by just looking how the spin correlations are present over larger distances, conditioned again on having a hole in between those spins or at the same side of the spins. So here's the kind of antiferromagnetically ordered system. So you see it goes from up, down, up, down, up, down. And whenever you have a hole in between, you see how this pattern is just shifted by one side. How this antiferromagnetic pattern is just shifted by one side because this hole just flips the whole antiferromagnetic domain by parity sign -1. Here's just the same data where I just took out this -1 staggering of the antiferromagnet, showing you clearly that when the hole is between the two spins, you get a different sign of the antiferromagnetic parity, whether the case when the hole is on the same side as the two spins. When it's not sitting between these two spins, you get the opposite sign of the antiferromagnetic parity. What's actually also pretty interesting, what was striking for us, is that these antiferromagnetic correlations even persist even if you have many holes between the two spins. So this is shown here. So this is the number of holes between the two spins. So let's have like 5 holes between the two spins, okay? And you can see that even for these large distances, the antiferromagnetic correlations remain. So even if you have many, many holes in between those two spins, they still want to remain antiferromagnetically correlated in this strongly doped Fermi-Hubbard chain in our system, okay? So let me connect this now to the notion of topological order that was now actually important for Duncan Haldane's Nobel Prize, how that is connected. So we said each time there's a hole, there's a parity flip in the antiferromagnetic background, right? So if we somehow could remove the holes, on the other hand, what we would actually find that this is a perfect antiferromagnetic in a fictitious space let's call this space squeeze space. It's the space where we would have removed all the holes from the system, we squeeze the system together, and then we would find actually a perfect Heisenberg antiferromagnet as in the undoped case, okay? And this is actually the essential notion of spin-charge separation. So if you look at it from a wave function level, and these are actually beautiful results from beta-ansatz solutions from Wojnarowicz in the 80s and Ogata and Shiba, which showed that if you write down the wave function of this state, it factorizes into a product wave function of spinless fermions, which basically define the position of your particles, times a Heisenberg antiferromagnet living on this fictitious squeezed space where those particles are. And this factorization of the wave function into this charge part and the spin part is really the true fundamental essence at the wave function level of spin-charge separation. Now you can measure that. You can actually do this pulling out of the holes if you can see them in the experiment like in ours. You can do that by introducing the notion of these string correlators. So what this string correlator does is that each time it encounters a hole, it flips this parity of the antiferromagnetic background by -1. So if you now correlate the spins on site SZ and SZ at distance d, if you take into account all the spin flips, you actually find a perfect antiferromagnet again, and this should give rise to this antiferromagnetic spin correlations of this doped chain. And that's actually very nicely written down. If you want to read about this, there are beautiful papers by Jan Zahn which explain this connection in a very, very nice way. So again, let me now connect this to our whole notion of order parameters, of how we characterize many-body states. And typically, we do this through this Landau paradigm of phase transitions, where we take these observables at two sites, x and y, and as we take the distance between those 2 points to infinity, this approaches a constant value. So that's a very common scenario, for example, for a ferromagnet, an antiferromagnet, a BEC, a condensate wave function, a BCS superconductor. For example, in a ferromagnet, if you tell me the position of the spin at some point here, I can tell you what the spins will be pointing everywhere in your system. Okay, the notion of long-range order. Okay. Now you can ask, are all of the phases of matter characterized by such kind of Landau paradigm order parameters? And of course, by now you should answer no, because we've seen, I've already introduced you an example in the last case where this is not the case. We have more general correlations in kind of strongly correlated many-body systems, where in order for this correlator to have a finite value of measuring the particle observable at point x and observable at position y, we need to also know what's going on all the particles in between those 2 points. Okay, this is the idea of what we call a string correlator. And if that goes to a constant value, then we say this has a hidden kind of order parameter given by this string correlator. Why do people say this is hidden? People say this is hidden because this was completely unimaginable that you could measure this. Okay, that's why people thought this is an entirely theoretical concept to kind of characterize correlated states of matter, because typically you cannot measure what's going on all your particles between the 2 endpoints where you actually want to do the measurement. Okay, but what I showed you with a quantum gas microscope, we can actually do that. We can precisely measure such spin correlators, because in a single snapshot of the experiment, I'm not only seeing what's going on at point x and point y, I'm seeing what's going on at all the points in between, and therefore I can evaluate these string correlators in experiment. So actually, there's a famous example in the case of the Haldane spin 1 chain where this indeed shows up. This is kind of, I've sketched it out here for the case of Bose-Hubbard interactions, but it doesn't matter. Imagine you have a spin 1 chain here, and in the case of the Haldane spin 1 chain, you have this, again, this hidden antiferromagnet, very much like what you've seen in the Fermi-Hubbard chain I've shown before. So there you have spin zeros, spin minus ones, and spin plus ones. Now, what's characteristic to this Haldane chain is that whenever you have a minus 1 here, the next spin, which is not 0, is going to be a plus 1. And when you have a plus 1, the next spin that's not 0 is going to be a minus 1. The problem is you don't know where the zeros are. The zeros can be everywhere on the chain. Okay, so that means in a 2-point correlator, you cannot keep track of these correlations. You need to know where the zeros are to reveal this hidden antiferromagnetic structure in the system. And by making use of these string correlators, you can precisely do that. And the string correlator, again, just removes those zeros. And then you see you just have the minus 1, plus 1, minus 1, plus 1 structure in the experiment. Okay, so now finally I have to show you that this really works in the experiment. So this is all good, but let's now show you that this works. Okay, so this is a spin correlation measurement now for an undoped chain, and we see the nice antiferromagnetic correlations. And now we have a heavily doped chain averaged over different doping values ranging from 40% to, actually from 0% to 60% doping. And you can see that beyond nearest neighbor spin correlations, all the correlators just vanish, which makes you believe there's absolutely no magnetic correlations anymore present in the system beyond this distance. But now if you evaluate the string correlator, what you can show is if you pull out the holes, all these systems, now you see these emerging antiferromagnetic correlations again. You see how you can restore these antiferromagnetic correlations living in the chain. It's just that they weren't visible to you because you weren't keeping track of this hidden antiferromagnetic structure hidden in these zeros in the system, in the holes in the system. But if you can measure the holes, you can pull them out, you can go to this squeeze space, and in squeeze space you see nice antiferromagnetic correlations that you see here, that for different doping levels we can recover this antiferromagnetic structure beautifully in the experiment. Okay, let me move on. How am I doing in time, actually? Good, okay, so let me move to the third topic, another topic. So if you haven't been, you can start again now and join me again. So the next topic I want to discuss is on many-body localization. And this is, again, very much connected to statistical physics and very much connected to the fundamental question, how come that we can describe a system by thermodynamics, statistical physics so well that we can usually do in many-body systems. So let's take, for example, this coffee that's served to us, milk, coffee. Yeah. Okay, you wouldn't be happy, right? And you wait a bit, and it's all mixed, and you end up with this. And the system we say would have thermalized. And after it's thermalized, from this state, we have no way of telling, for example, that it actually came from this original state here. Okay. So what I want to tell you now is actually a case where this does not happen. We want to look at scenarios where this typical thermalization does not occur in the system, and the system actually can be prepared in a way such that if you prepare such a non-equilibrium state like this one, it can in principle persist for indefinite amount of times. Okay? So that means that no thermal state is reached because the thermal state has no memory of an initial kind of configuration per definition. And that means actually that if we're not in a thermal state, all our statistical physics approaches fail. Okay? Now that's why I think why people are so interested in this field, because it means we really have to derive many things from scratch and think about the notion of phase transitions and statistical physics in this context completely new way. Let me put this a little bit more on formal grounds, what I'm saying. Let's imagine you have an isolated quantum system prepared in some eigenstate of the system. Let's say this is our total system. It's isolated from the rest of the world. It's in some eigenstate of the system. And what you typically find is that if you take a subsystem of size L, which is smaller than the entire system here, you will find if you trace out this remainder of the system, you find that the subsystem typically looks like a thermal density matrix. And that's, of course, the reason why typically thermodynamics works so well. So the remainder of the system acts like a heat bath for the subsystem, giving rise to this thermal density matrix that we typically encounter. That's what underlies what people call the eigenstate thermalization hypothesis. But as the word hypothesis says, this is a hypothesis. We don't have a proof for that. But it actually looks like for most generic quantum systems, this is true. Of course, we know cases where this is not true. One prominent example where this is not true is our integrable quantum systems. And integrable quantum systems typically have so many constraints on their dynamics that this cannot be fulfilled. But integrable systems are typically always fine-tuned, so they might not be relevant so much in nature, because if you go epsilon away from the integrable point in your Hamiltonian, you immediately come to a thermalizing system again. But the question is, are there more robust scenarios where this is indeed also the case? And this is now where the field of many-body localization comes about. That basically, there is a notion of emergent, self-emergent integrability occurring in these systems that gives rise to non-thermalizing behavior and failure of statistical physics for interacting many-body systems. And this goes back to pioneering work by Boris Altschuler's group in 2006. And I think good reviews, if you want to start reading into this and connections to quantum information theory, are these two review papers here from David Hughes' group and Ehud Altman's group shown here. Now, for a long time, this has been a purely theoretical field. Now, more and more experiments are emerging on cold atoms, cold ions, and V-centers. So it's really getting a very exciting field also for experiments to work on. So what can we do to make such a system? What ingredients do we need? Well, we need an interacting many-body system. We need something that's isolated from the environment, because if we're connected to a thermal reservoir, we're going to thermalize by definition. And so cold atoms are good in these two first respects, but we need a third ingredient, and that is disorder. Okay? We need also disorder to be present in the system to realize these many-body localized systems, and then I'll show you ways how we can probe for them. So the way how we create disorder is by using these kind of digital mirror devices. So these are just probably the same thing that's in this small projector down here, just small micromirror arrays which we can turn off and off, and we can use to make basically arbitrary patterns of light, like these two reservoirs, for example, connected by a single wire, a light wire, or arbitrary light structures. But in the case I want to show you now, we want to use it for even something much more simple. We just want to make a disorder pattern. Okay, so we just turn on these pixels, these DMD pixels, in a random fashion. Their random kind of pixel structure is convoluted with the point spread function of our imaging system, and that's what our atoms see as the disorder distribution that we can now fully control and project onto the atoms. So here's the probability distribution of the disorder at a given lattice site that we have on our atoms. And it's in our full control. Now, how can you show that the system is many-body localized? Well, let's think again of this coffee and milk example, and trying to show what you want to show for a non-thermalizing behavior. It's actually easier than showing thermalizing behavior. What you want to show that you find one observable which is non-thermal for long evolution times. Okay? So what we set up in light of this, we take this initial Mott insulator, which had unit occupancy in a circle of the radius that you can see the contour here, and then we removed half of the particles to this side. Okay, so we created this very sharp domain wall. It's like this milk-coffee interface, but now just particles and no particles. Vacuum and unit-filled lattice structure. And this is a single shot with a quantum gas microscope, and this is averaged over 100 shots. Okay? And now what we can do, we can let this system evolve, and then we can do this over 250 tunneling times, for example, and you can see how this, for very long tunneling times, it evolves basically into this symmetric cloud, and we can actually fit this with nice thermodynamic fit functions, which would tell us that this has become kind of a thermal system. I can characterize it by a temperature, which very well agrees with the initial energy that we have in the initial system here. So everything looks nice and thermalizing here. However, if you add this order, you can be in a situation where this occurs for long evolution times, where you evolve into this structure where you see it did not evolve into the entire system. It did not become symmetric. There's still some memory of this initial domain wall, even for long evolution times. And if you have this memory of the initial state, this cannot be a thermal state. And it tells us something about, it gives us an indication that we've entered a many-body localized phase. Now, the way to characterize this is just to take the number of particles to the right of this domain wall, minus the number of particles to the left of this domain wall, divided by the total number of particles, which we call the imbalance of our system. And if that imbalance is 0, the particles have spread out completely. We're in a thermalizing ergodic phase. And if this imbalance is non-zero, then we're in this many-body localized phase where the particles basically do not still have this memory of the initial state and do not thermalize. And you see actually in the experiment, there seems to be a rather sharp point where this transition from the ergodic to the MBL phase happens. So around a disorder strength of 6 to 7, we see this transition from ergodic to MBL phase. We've also looked, what happens if you do this for different interaction strengths in the system, and you actually find that for different interaction strengths or densities, effective interaction strengths, as you change the density of your particles going to more non-interacting systems, this critical point seems to shift to lower values of this order. And I want the experts of you on Anderson localization for non-interacting particles, this is what you expect for the non-interacting curve. This is the white points here coming from a simulation, because we can't turn off the interactions in the experiment, unfortunately, in this experiment. But you see how strikingly different Anderson localization is from the interacting case that I show you here. Okay? Anderson localization occurs for arbitrary small disorder depth, you localize in 2 dimensions. So for epsilon disorder strength, you localize, and you get immediately the finite imbalance that I show you here. Whereas for kind of the interacting system, you see that you get this completely different behavior, that you need to go to rather strong disorder strength to localize the particles in your lattice and to see this many-body localization phenomena. So something completely different from the Anderson localization case that I've shown you before. One thing, maybe one final thing that I would just like to show you, what's become a hot topic in the field is how stable is this localized phase actually to the presence of thermal baths. I told you in general a big infinite thermal bath will kill localization immediately. Okay? But what if we have small baths? Do they kill the system? Do they kill the localization phenomena? Or is the system still stable to this localization phenomena? And this has been, I think, to date an unsolved question. What happens actually. But the question is kind of sketched out here. So you have your localized system, you couple it to a thermal bath, and you ask now, is this localized system going to localize this guy here? Or is this thermal bath going to destabilize, delocalize this system up here? When these two are finite, have finite size. So the way how we can address this question is actually a nice setup in our disorder potential. We can tune this disorder potential that I showed you to this magic wavelength of 787.55 nanometers. And that means that actually the light shift, the polarizability of our atoms is very different for these 2 spin states. So for a spin-down particle, we have a 0 crossing in the light shift, meaning that whatever light we project on them, they just don't see it. They just don't see this as a potential. So it's completely flat. Whereas the particles in this other spin state, actually they can be exposed to the disorder potential. So we have an interesting configuration where one spin component sees the disorder and the other spin component does not see the disorder. Okay? And now we can ask what happens now in the experiment when we do kind of an experiment like this. So we set up an initial what we call charge density wave where we occupy only even sites in the experiment. And then in order to populate the other spin component, we can just do Rabi flops and just create a controlled fraction of these spin-up particles that do not see the disorder potential. So that's nice because I can change the ratio of spin-downs to spin-ups in a completely controlled way. I can change the ratio of particles that see the disorder and that don't see the disorder in a completely controlled way. And so far, first experiments that we've been seeing, first of all, for if we have no kind of delocalizing particles in the system, we see that, again, for low disorder strengths, this charge density wave relaxes to 0. We have an ergodic phase. Whereas for larger disorder strength, we get this plateauing behavior. And now we can observe this even out to 1,000 tunneling times. Okay, so this gives rise, tells us there is an indication for an MBL phase. And what we now find that as we change the spin down population, this ergodic component that we have in the system, it seems to be the case that actually this just pushes the MEL transition to higher disorder strengths. So if we start to have a certain delocalizing ergodic component in the system, we're still able to push the whole system into a MBL phase. We just need a higher disorder strength to do so. Now, whether that's always the case, we don't know. So what the phase diagram actually looks like is an open question. So we just, let's say, have here, let's say, an ergodic phase. And here's the MBL phase, right? And now I'm having here my disorder strength on the vertical axis and my polarization on the lower axis. And whether there's always a point, whether I can always increase my disorder strength above a certain threshold of the polarization to reach the MBL phase, or there's a certain point where I just cannot do this anymore is an open question, which we hope we can answer soon with these experiments. All right, I think I should not go into the last topic, but because I'm exhausted too, actually. Okay, so let me just skip the Rydberg topic. I can tell you more in private about that. Let me just come to the conclusion and just hope I could tell you a little bit of the most recent experiments we've been carrying out with these cold atoms and lattices. On the one hand, looking for topological effects in the single particle systems, topological effects in many particle systems, using these new ways of quantum gas microscopes to characterize these many body states in completely new ways, and actually exploiting that to look at really fundamental questions in a completely new field of physics in this many body localization field. And of course, we hope there are many more connections we haven't explored yet, but we can explore in the future. And with that, I would like to thank you for your attention.
One simple one. I mean, at some stage you said that you can not only see the atoms but also measure currents. Mm-hmm. How do you do that? I mean, just both at the same time?
No, not at the same time. You have to make a decision that would be a problem. No. So what we do if we want to measure the currents, let's say we have a lattice, okay, and let's say I want to measure the Y currents. What I do is I cut these bonds here and make double wells, isolated double wells now out of my whole system, but I do it in a sudden way, okay? And then I look at the Josephson oscillations in these bonds, and the phase of the Josephson oscillation will tell me what the current operator, what the measurement value of my current operator is if I look at a specific point in time, okay? So the idea is to start with your full lattice, separate it into double wells, make use of Josephson oscillations in these double wells, and these Josephson oscillations will tell you the measurement value of your current operator if you observe then, for example, the particle occupation at the right point in time. So that's the basic idea. Yeah. But you have to make a choice, of course. Then you made now your current measurement. It's not compatible with the particle measurement anymore again, of course.
Okay, so I have another question. I mean, you're able to measure a lot of things, but behind that, You assume that you know the Hamiltonian.
No, not really.
So tell me, how do you measure the Hamiltonian?
The measure the Hamiltonian. Well, I'm not saying I'm measuring.
That's my question.
I'm not measuring the Hamiltonian. What I'm saying, I'm measuring basically the wave function or the density matrix.
Okay, but
so actually, so in the what I've shown you. So in this, let's go back to what we measure. Okay. So actually, what we measure. Where is it? This one. This is the slide. Okay, so what we actually, okay, we measure, we make a photo, it collapses onto a certain constituent. So we see in a single shot, we see this particle configuration. Then I repeat the experiment, I see another particle configuration. So in essence, what I can measure then is the probability distribution of the different particle number arrangements. So it's basically the prefactor squared of those particle configurations.
But so answering my question, could you think of measuring in some way, I mean, at least some matrix element of the Hamiltonian? Because, I mean, you agree, if you measure all the things, but you would have no idea of what is the Hamiltonian. Naturally, you have ideas. But if you would have no ideas about what is the Hamiltonian, this wouldn't be terribly interesting. So could you check, in some sense, as much as you could on the Hamiltonian?
Yeah, I think, of course, typically in cold atoms, the problem is the other way around, that we know the Hamiltonian very precisely, or we believe at least we know it very precisely, and we don't know what the states, the emergent states are. What you're asking, I think, should be possible also, but it requires, of course, different measurements on transition, as you say, matrix element measurements between different states. So I haven't thought carefully about that, but it should be possible too. But I would say typically the scenario we deal with cold atoms, that our Hamiltonian is extremely well defined, actually. You don't believe it?
No, it was checking.
No, sure.
You're checking a lot of things, and very often you know the answer, you check it's true, so you could have
here there are many examples where we don't know the answer. For example, in this MBL dynamics that I showed you in 2 dimensions, there's absolutely no numerical method that can handle this to date. We have absolutely no clue in numerics what's going on here. Okay? Even 1D dynamics is so difficult that already in the 1D dynamics experiment, the theory, actually Fabian Allé's group in Toulouse, actually, they're doing one of the best exact diagonalization simulations, largest scale simulations, but that's also limited to 14, 15 particles. Yeah? And then you're always kind of finite size limited in the system.
Actually, I want to understand one point here, probably it's related. You have the lattice. Mm-hmm. But actually, the atoms are not the ones that make in the lattice. So when you see in the crystal, if you take out an atom, then the potential changes.
No. That's a very important point.
Right.
The potential is made by our light fields. So this comes back to my first slide here. So here. So this is the lattice. This is a fancy lattice. Take a square lattice. Look simpler. This is the light field distribution, and we control it just through the laser beams.
Yeah, right. That's
so the atom has no role in creating this lattice structure.
Exactly.
Yeah. So if you remove an atom, the lattice structure is still there.
Yeah, the lattice is there.
Yes.
But
you don't like that, or
no? In the crystal.
Yes.
In some of the cases you discussed, actually, the atom, it's involved in the potential itself.
Yeah.
So when it moves and it has a defect, it changes actually the whole thing.
That's true. You can have situations like that also in the cold atom context, not in this context that I showed you here. But I think this is, first of all, a good situation also to be in, that you know your lattice structure is always fixed. What you want a back action of the movement of the particles on the lattice. You can create different ways how to do that. You can put your particles, either create the lattice in a cavity, for example, or you can have another species, another atom component that forms now through its interaction with the other component a lattice structure. And now, of course, if these atoms move around, they will feel this lattice structure. Actually, I didn't comment on this, but maybe here's actually an example of how this looks. So here is, remember this relaxation dynamics I showed you, where with the 2 spin components. One sees the disorder, the other one does not see the disorder. Okay? So one does not, let's say, see this. So we have kind of an initial stripe structure there through the atoms, where both the spin up and down atoms are. And this creates a positive imbalance here that we see here. Now you see the component that does not see the disorder potential, it immediately wants to spread out, but actually goes into a negative imbalance value. And the only reason why it goes into a negative imbalance value because it sees a lattice structure through the other atoms and wants to move into the minima of the other atoms. So the density wave of the one component that sees the disorder, that tries to stay localized, tries to stay in this charge density wave, creates an effective potential for this other component.
These are van der Waals interactions between that?
These are actually just van der Waals short-range interactions that give rise to this S-wave scattering.
So yes. This is superposed with the other lattice.
Yeah, that's right. Yeah. So there are ways to do what you want to do. But a priori, for many of the situations we have, it's actually interesting to just have the lattice fixed by itself and no back action, and then just look what happens if you dope the system, if you change parameters.
I was wondering for the MBL phase that you've shown, you have this interface which is sharp. Have you looked at the statistics, the time statistics?
Yeah, no, that's a good question. Not yet, but I think that's very interesting.
What kind of distribution is it connected to? Is this, fluctuations à la Cardar, Parisi,
yes,
or
very
whatever?
Good. Yes. Very good question. No, we have not looked at it, but what you're asking is basically this. We have the single shots. So these are the single shots how this domain wall evolves. So we can now make a histogram of, let's say, for example, actually see, it's interesting, this particle here made it very far from the domain wall, but the others didn't make it so far. So we can have a statistical distribution of how the particles have moved away from the domain wall. Yes, we have not looked at it, but I think that you're completely right. There are many powerful ways how to analyze this data even better and extract maybe more interesting features out of that. Yes.
Thanks. So for NBL, I think one of the metrics which is very interesting is to know how the entanglement between part A and the rest is evolving in time.
Yes.
Especially it should be slower, logarithmic in time, I think, compared to linear in time for the ergodic phase. So do you have any future ways to measure this entanglement?
Well, so there is a way, Markus Greiner showed in his experiments how you can do this for very small systems, how you can measure entanglement entropy. I just don't believe it's feasible for a system of the size we're talking about here or hundreds of particles. It's just extremely complex to measure, extremely many measurements that you need to do that. But I think there are other quantities that we can look at, and it comes back maybe to Christoph's question that are related to the entanglement entropy growth. That is, for example, how the fluctuations in your imbalance trace, for example, in your time trace, how they evolve as a function of time. So it's not the average value of this imbalance, which gives this density wall, but the fluctuations, how they evolve as a function of time. So people have shown that these are also linked to kind of, at the fundamental level, to this dephasing dynamic, which gives rise to this logarithmic T entanglement entropy growth. And those are things I think with the quantum gas microscopes we can indeed should be able to measure in experiments. Yeah, absolutely.
Okay, if there is no further question, thanks again, Immanuel Bloch, for this very